to start. Yep, and I will head over to screen share. I will share the screen, and we are going over to my screen. Can you see the screen? Brilliant. So that at least works. Fantastic. Excellent. So let's make a start. Let's talk a little bit about electrophoresis and the principle. And in a way, if you like, the principle is exactly the same for DNA, RNA, and proteins, because what we do is we will have a charged molecule. So a charged molecule will travel, will move, let's call it will move in an electric field. In an electric field. So that is really the big concept behind it. I have posted a website with DNA agarose gel electrophoresis, the stuff behind it. Has anyone had a chance to look at that? Was that useful? I think it is also up on Moodle. Kami says they found that useful. Good. So please have a look at it. So what we have here, charged molecule, and we can either use DNA. How is DNA charged? What is the charge of DNA? How is DNA charged? Electrically. It is Oscar absolutely, sorry, Dana, absolutely right. It's negatively charged because of the what groups? And somebody is not muted. The phosphate groups, exactly. So DNA is always negatively charged. We can also do electrophoresis with RNA. How is RNA charged? How is RNA charged? And why is there a question mark? Of course, RNA is also negatively charged. Why? What group gives it a negative charge, RNA? It's the phosphate group. Absolutely right. So these are negatively charged basically at all times because of the phosphate group. And therefore, DNA molecules will move from the negative side to the positive side in an electric field. So DNA or RNA molecules will move from negative to positive because the molecules itself are negatively charged. Yeah, does that make sense? It's not rocket surgery. And the concept is that we let the molecules move, let molecules move in a matrix, and this matrix is a gel. And this gel consists, in the case of DNA and RNA, it consists of a compound called agarose. It forms pores, quite large pores. And the DNA and RNA molecule have to squeeze through the pores. So squeeze through pores. But they all move in the same direction, from negative to positive. They have to squeeze through the pores. Big molecules move slower. They find it more difficult to get through the pores. Small molecules move faster. So when we stop the whole process, what we will, and then visualize the DNA or RNA, what we will find is, so here is our starting point. That's the start block. And what we will find is that the molecules move like that. And the molecule that has traveled the furthest, so if this is the start here, the molecule that has traveled the furthest, obviously, is that the largest or the smallest? Is this pink one, is this the largest or the smallest? Kami says it's the smallest. Anna confirms that. So yes, this is the smallest because it can move very quickly. Whereas this one here, this is the largest because it can't move that fast. And actually what we can do is we can sort of determine how far a molecule has moved depending on its size. How are you going to do that? Well, what you can do is you can measure how far a molecule has moved. So what you do is you just take a ruler and measure the distance from the start to the band. So you would do these measurements like that. And you get a sort of a nice set where you can look at how far has a molecule moved. And if you know, for example, if you know the fragment sizes, if you know how big these fragments are, then you can sort of create a standard curve. How can you do that? Well, let's say this molecule here has 10,000 base pairs. This is really big. This molecule here has, say, 1,000 base pairs, smaller. And the smallest one, let's say that is 100 base pairs. If we know that, all we need to do is we need to measure the distance from the start to the band. And then we could, in theory, we can nicely do a sort of a standard curve. And the way we would plot that would be, let's see if I can plot that. What we would plot in a way is we plot, what do we do on the, what is our independent variable? the variable that we have control over. What would go on the x-axis? We can either have fragment size or distance traveled. What should we plot on the x-axis? Yep, exactly. We would put down the fragment size. So here we've got 100. Here we've got, let's say, 1,000, and here we would have probably 10,000. Oops. So let me write this. 10,000. And here, so that would be the fragment size in base pairs. And here on the y-axis, we would plot distance traveled. And what we will find, if we do exactly that, we would find sort of a very weird plot. It would look like something like that. Oh dear, my curve is really wobbly. It's not much better, but we would get something like that. Doesn't look like a straight line, does it? The trick here is that it is not linear. That is not a linear thing, a linear relationship between fragment size and distance traveled. Actually, it turned out that the relationship for basically any gel electrophoresis, and that can be protein or DNA, doesn't matter, for any gel electrophoresis, turns out that the relationship is depending on the logarithm of the fragment size, logarithm of size, and this then gives a linear relationship with the distance. So if we, instead of plotting this guy, this graph here, instead, if we plot the logarithm, and you can basically use whatever logarithm you want. You can use it to the base of 10 or 2 or whatever you fancy, but it has to be a logarithm. So if we plot logarithm of fragment size versus distance, then we would get a completely different picture. So what would be if we do logarithm 10 of 10,000? What would give us, what would we get in this case? What is log 10 of 10,000? Anyone? Yep, that's right. So we would get 4 for 10,000. It's basically you count the zeros, right? What is logarithm of 1,000? Yep. And I don't ask you for 100. So if we had a logarithmic scale with 2 3 and 4, we would get a nice straight line. So we have a linear relationship between the log of the fragment size and the distance. If we just simply plot fragment size, like we've done here, versus the distance, we get a weird curve. Does that make sense? And if we've got sort of a standard curve, and you know now, because of the last session in BI 308, we know how we can do such a standard curve. By the way, is that a positive or negative correlation that we see here? Absolutely right. It's a negative correlation. Absolutely right. And what's wrong with an asymptotic graph? Well, you can't do any decent analysis if you don't have a linear relationship. That's the problem with it. Because all you really have is you have these points here. And because it is a linear graph here, a straight line, you can interpolate, you can draw a straight line. But if you've just got data points like this here, let me remove that. So you've just got these data points here. How do you draw the graph? So always go for log fragment versus distance, because then you get a nice straight line. And let's say you've got a fragment that has traveled a certain, oops, where am I? Why did that happen? Am I back? Yeah. Is that all right? Okay, good, thank you. If I have a fragment that, for example, has traveled that far, here, I don't know exactly where it hits the graph. But here, it's very easy. I can immediately see this, and I can get Excel to do the line of the best fit for this linear thing, for the linear regression. I get my gradient, I get my intercept, and I can do the calculations. So I can immediately see how far this band has traveled and the base pairs. Actually, I can't do the base pairs because this gives me only the log of the fragment size. How do I convert the log into base pairs? What do I need to do? To eliminate, to get rid of log, let's say if it is log to the base of 10, for base 10, we always do base to the power of. Absolutely right. So it would be 10 to the power of this log size if we are using log 10. because 10 and log 10 cancels out. If I decide to plot it by the natural logarithm, ln of size, which I could do, which also would give me a straight line, then I would need to do e to the log, to the ln of the size. But most common is log 10 for the fragment size. Okay, happy with that? So that is DNA, and DNA is easy to deal with. Why log 10? It's just, it's the easiest to do, to calculate. But if you really want to do log 3.1506, there's nothing that speaks against that. It's just rather unusual, and you might get some funny looks if you do it. But as long as you are in the log range, as long as you use logs for plotting and not the direct number, then you will always get a straight line. Some people use ln, but they are really in the minority. Usually it is log 10 that people use. Okay, so that was DNA and RNA, and we can very easily determine then how big a fragment is. And I think I have an exercise on the website that I emailed you about the DNA gel electrophoresis. So that was DNA, right? And you will do a practical with my colleagues soon, where you create DNA fragments and where you need to find out, are they of the expected length? And that is the way you do it. You use DNA gel electrophoresis, and the fragments will move, and then you have to find out what is the fragment size. I don't think it was. I put it on the on Moodle yesterday, I think. But if people want, I can send out a general email for everybody who's doing BI 300 with the website. And if somebody has the link to the website, I can also post it in here, the link to the website. Would that be all right, Donna? I'll just post it there. Now let's look at protein electrophoresis, because people told me that they struggle with that. Now, with protein electrophoresis, it works exactly in the same way. We have a matrix in which we run our proteins. In this case, the matrix is not agarose, it is polyacrylamide. And polyacrylamide forms smaller pores because proteins are usually smaller than DNA or RNA molecules. But we still have pores. Now, with DNA, it was pretty simple because DNA is always negatively charged. And so is RNA because of the phosphate group. How are protein charged? What is the charge of a protein? What do you think? What is the charge of a protein? You are absolutely right. It depends on the side chains. So we can't make a general rule. And if we apply an electric field, we have basically three options. It could be positive, it could be negative, or it could be neutral. So if the protein could basically move in either direction, towards the positive side, or it could move towards the negative side, or it just simply stays put. Cami, thank you very much. That is exactly the link that I was talking about. So with proteins, we don't know which direction they are moving. So therefore, if we want our proteins to move always in the same direction like DNA, we need to force a charge on them. Of course, we could have the protein totally unperturbed, and we are not forcing any charge on it. So no charge forced. No charge forced. So we leave the protein basically in its natural state. Then we would talk about a native gel electrophoresis. Gel electrophoresis. This means we just leave the protein as it has been created. We don't mess with it. We don't destroy it. The protein is still biologically active. So if it is an enzyme, it hopefully would continue with doing what the enzyme does. So native gel electrophoresis leaves the protein untouched. But usually it doesn't tell us a lot. However, we can force a charge on the protein, and we do that by we denature the protein. Denature. We usually use heat. So we heat up the protein because we know that when something is heated up, it moves faster and the protein sort of unfolds. And then we add sodium dodecyl sulfate, SDS, because SDS is negatively charged. And this SDS will then attach itself to the protein. So I draw the opened up protein. So here, before we start with the protein, that's nicely folded. We heat it up, the protein unfolds, and the SDS is attached to it. And we have loads and loads and loads of SDS molecules attached. And each of these SDS molecules is negatively charged. We will break any interactions that are non-covalent with this method. So if we've got, for example, another molecule attached to it here, then with this procedure, we will split everything that is not covalent. So we will get, let me draw it in a different way. We will get the black protein and we will get the pink protein separated from each other. So this method rips apart everything that is non-covalent. So non-covalent bonds, covalent bonds will be disrupted. So for example, if we have, what is a non-covalent bond? Give me some examples for non-covalent bonds. Yeah. Ionic bonds. What else? Hydrogen bonds. And if there is a sort of, dipole, yes. And hydrophobic, yes. Although it's not a bond, but if there's a hydrophobic interaction, yeah, all these bonds will be all these interactions will be destroyed. What about a disulfide bond? Is disulfide bond covalent or not? So I draw a disulfide bond between two cysteine residues. Is it a covalent bond or not? The way I have drawn it. Yes, it is. So disulfide bonds will remain if we do this treatment. Does that make sense? We price apart everything if it is non-covalent, but covalent bonds, like disulfide bonds, will stay. Oh, ionic bonds are 10 times weaker than a covalent bond. Covalent bonds are brutally stable. Ionic bonds are far less stable than that. So what do we need to do in order to break disulfide bonds? What we do is we use exactly the same procedure as above. We denature the protein with heat. We add SDS, and this time we add a reducing agent. Reducing agent. A reducing agent will cleave disulfide bonds. It will do this. It will cleave the disulfide bond, and very often we will use a compound called beta-mercaptoethanol. Or just beta-ME. Very good questions. What we do when we just use SDS, we break inter and intramolecular interactions. And if we do that in the presence of a reducing agent, we again break all the inter and intramolecular interactions. But in the presence of the reducing agent, we also plus break disulfide bonds. Does that make sense? So we can run a gel native, but that's very tricky to do. And it only tells us how big something might be. So that's usually not terribly useful. We can run it as in the presence of SDS, and we can run it in the presence of SDS and beta-mercaptoethanol. This would be actually called oxidizing conditions. This would be reducing conditions because we have got the reducing agent in there. Okay, so we can do these both things. And we can get, by running a gel, we can get information about the protein. And now here, let's play a little bit of detective. And I show you already who was the killer. I show you the protein that I have in mind. It's a complex protein. It is called clapperase because it destroys basically human life, and it destroys students. And this protein is made up of the following compounds. It has a core unit which is 100 kilodalton big. This core unit has one disulfide bond in it. It is also connected via a disulfide bond to another unit, which is 50 kilodalton. And as it happens, this 50 kilodalton protein is associated with another subunit that is a 25 kilodalton. And actually, this has a brother, and this is connected by a disulfide bond. So here, this is a non-covalent interaction. But it gets worse. This thing is also connected through non-covalent interaction, yet with another 100 kilodalton band, which has an internal disulfide bond. Via disulfide bond, it is again connected to a 50 kilodalton band protein, which is connected 25 kilodalton and 25 kilodalton, and these two are connected by disulfide bonds. So let's do a little bit of color coding. The 100 are here. We have a yellow, which we probably won't see. That's the 50 and 50. And let's do a pink one. Which looks like that. So obviously, this protein, or this is a protein complex. And we see that the proteins not only have primary structure or secondary structure, they also have tertiary structure, and because we've got several proteins combined, it is a quaternary complex. And it is made up of green, yellow, pink. So we've got 3 different proteins involved. 3 different protein types. 3 different proteins. And the complex itself is made up of 1, 2, 3, 4, 5, 6, 7, 8 subunits. Does that make sense so far, what I have done? Yeah? So you can follow. Now, big question. Big question. What is the molecular mass? And you know what kilodalton means. It means just 1,000. What is the molecular mass of this complex? How many kilodalton? Is Kami right? Kami says it's 400 kD. Anyone else? Absolutely right. It's 400 kD because we just simply add them all up. So let's run this protein complex on an SDS gel. Actually, if we run this complex, would we know, so without the SDS, no SDS in the first place, how is this complex charged? Do we know? What is the electric charge of this complex? We don't have a clue. So it could run either to the positive side or the negative side, or it might not run at all. So what we do is we run this guy in the presence of SDS, and SDS only. So what would we observe? We would obviously break all the interactions that are non-covalent bonds. So what are the fragment sizes that we would get if we run it with SDS only, or under oxidizing conditions? What are the fragment sizes that we get? Some good answers here. So what we would get is, we would get the 150 kilodalton. We would break basically this interaction here between the complex, and we would break this interaction here. So we would get this one here. Then I'm just circling, and we would get this bit here. And we would get this twice. Absolutely. So we would get 150 kilodalton, and we would get 50 kilodalton. So we get a band like this and a band like this. We would not necessarily know whether it's twice, but if we know that it is, if we already have determined that it is a 400 kilodalton complex, we could easily figure out that it is made up of 2 times 150 and 50, because this gives us 400. So it would be pretty much in line with what we would expect. Okay, so that's under oxidizing conditions. What would happen if we have SDS plus beta-mercapto ethanol? No, you can never assume anything, especially when it comes to proteins. You would need different methods to analyze that. So, for example, had I told you that this protein complex was actually 800 kilodalton, we might have had the whole thing 4 times. But in this case, it nicely fits. So what would we get if we do it under beta-mercapto? So we break these interactions like we had before, but now we also destroy the disulfide bonds. What about this disulfide bond? Would we, where the arrow points, would we destroy that? In the 100 complex? Yep. Would it have any impact on the band size? Most likely not, because it is just an internal disulfide bond. So we would not necessarily see a massive change in where the protein is. But what we get is, obviously, we get 100 kilodalton protein. That's the green one. Oh, let me try to use the appropriate colors. So we get 100 kilodalton band. That's the green one. Do we still get the 150? The 150 has been destroyed. It has been split in the 100 and in the 50. So we would get, oh, probably can't see that properly. Let's do this one here. We would get the 50 kilodalton band, and we would get a 25 kilodalton. So 100, 50, and 25. Does that picture make sense? Now, the If, you mean if there is, for example, a second disulfide bond in the 100, actually it doesn't make a huge difference. It will still stay as a 100 kilodalton band. It won't change. The true experts in gel analysis can probably tell whether there are some internal disulfide bonds that have been cracked with the beta-mercaptoethanol, but us mortals, we are not too worried about that. So internal disulfide bonds are also opened, but they won't manifest themselves in a massive change in the mobility in the gel. One last question. Is this 50 kilodalton band that we got here, is this the same as this 50 kilodalton band? Are they the same bands? Is this equal sign right? Are they the same band? Absolutely not. They are not the same bands, because here the 50 kilodalton bands, in this case, was the combination of these two pink ones, whereas here, in this case, this 50 kilodalton band is actually derived from this one here. Absolutely. That's absolutely right. Well, there is a true 50 kilodalton band in, well, there is 50 kilodalton, but this is the two here stuck together, held together by the disulfide bond, which we don't crack under oxidizing conditions. So this is basically how the gels would look like for this protein complex when we run it either under oxidizing conditions or under reducing conditions. So this would be reducing conditions. And you see, we get a lot of information about our protein complex by doing these two different conditions on a gel. And the nice thing is actually you can run a protein gel, and it looks a little bit like that. Similar to the agarose gel, you have a start. Here we are negatively charged, here we are positively charged. All proteins are, because they've got the SDS in it, will move in this direction. And we can run it under reducing and under oxidizing conditions. Or let me do it the other way around, because we've done that. We run it under oxidizing conditions or reducing conditions on the same gel. And we would get, in one case, the oxidizing conditions like that. In the reducing, we get a pattern like that when we visualize the gel. So I can immediately say that this band here must be a combination of two bands held together by a disulfide bond because it disappears. It's completely disappeared here. So there must be two proteins held together by a disulfide bond. And very often when we work with proteins, this is, this is what we get. This is the picture that we get. And now we have to play detective and try and figure out what is the most likely combination of our protein complex. And there are a few other methods that we can apply, but that is really the bread and butter of playing detective with proteins. Does that make sense? Are you a little bit happier with electrophoresis? And do you understand the reason why we use, for example, SDS and why we use beta-mercaptor? Yes, yes, and yes. Fantastic. Actually, when you are in your final year, you will do a module on protein structures. And this is actually a problem question from the final year, where you have to propose a structure or a composition of a protein complex just on the basis of an SDS gel oxidizing and reducing conditions. So what you're doing here already is final year stuff, but I thought I can do that because, you know, I think you can cope with that. If there are no further burning questions, thank you very much for watching. And if you've got any questions, email me or put something on the group chat or here on the chat in Teams, and I will try to respond as quickly as I can. So thank you very much. And was that useful, the session? Good. So thanks again, and I shall see you on Thursday for another installment of BI 308. Take care, be good, and don't do anything I wouldn't do.